And the red one?
Yeah. Sure.
Recording, perfect. Thank you.
Is that all right?
All right, thank you. All right, so I want to prove that for every n, P of n is true. So what does it mean? That means I need to prove P of 1. What else? 2. What else? P of 4, and so on. Is that what I need to prove? But I will trade my assignment. And that's what's the question. Is it okay to trade your assignment and prove something else? Would that suffice? And instead of that, so assign this. This what's assigned. But I will prove this. And you will tell me if if you are okay with it, if you will accept that. I will prove this. I will prove P of 1. Then I will prove that P of 1 implies P of 2. I'll prove that P of 2 implies P of 3. I will prove that P of 3 implies P of 4. I'll prove that P of 4 implies P of 5, and so on. So I'm changing my assignment to this one. Would you accept this as good enough to guarantee correctness of this, yes or no?
What if I said no?
As I said, this is politics. Now I'm trying to sell it. If you say, no, that's it. I'll just tell you, use some other mathematics. There are people that don't accept this and do alternative arithmetics and all kinds of things. So generally, here is where I kind of think it's plausible to say yes. So I'm trying, this is political work, no math. So here it is. Look at this. Because I'm saying the following. Did I check P of 1, yes or no? But then if P of 1 implies P of 2 and P of 1, according to modus ponens, what will that give you? P of 2. But now you already have P of 2, and I proved P of 2 implies P of 3, according to modus ponens. What will those two give you? P of 3. And then P of 3 implies P of 4, and P of 3 will give you, and so on. So generally what this looks like is the following. There is a machine like P of n implies P of n plus 1. And then you feed 1, and this machine, according to modus ponens, produces what? 2. And then you feed that 2, and you get 3. You feed, so whatever you get, you kind of connect it with the hose up there, and the machine keeps running and covering all the numbers. Do you agree? If you want 55, if I repeat this 55 times, you will get P of 55. And that's basically the principle of mathematical induction. So instead of proving the
I was just wondering, would there be like a minimum for how many you need to prove? Like maybe like P1 to P2?
No, I need to prove all these, all of them. Yes, and by analogy, I say, why would this column give you this column? Wherever you want. If you want 1,000, actually when I repeat this 1,000 times, it's kind of to be expected that that's what will happen. So instead of proving for every n P of n, what will I be proving then? I'm proving the following. And that's principle of mathematical induction. I need to prove what? Number 1, I need to prove P of 1. It doesn't have to be 1, whatever your starting position is. And then what? I need to prove all these implications. So how do they all look like? P of k, let's call it k, just psychologically. For every k, P of k implies what? Here it is. And very often, and that's principle of mathematical induction. If you prove these two things, then I will accept like you proved the original statement for every n P of n. So people talk about it as a domino effect. So you generally put the dominoes, so it looks like this. There are some animations, but we're not going to do too many videos today. So if you think of this as dominoes that are, they do all kinds of those tricks in high school. How do they call it? There are two names on it. Whenever one thing does the other, and then second one put. How do you say? Rube Goldberg machines, yes. So generally, one thing affects the other. So what happens? Here are the dominoes that are close to one another. And what do you need to do? You actually want to show to put them all down, to cover them all, to have proof for all. So what do you need to do? To make two things. One is to push one of them, and what else? To make them close enough so that whenever one falls down, by falling down does what? Pushes the next one. And what will that do? Will all the dominoes go down? And that's basically what principle of mathematical induction says. It says what? It says prove that you can start and prove wherever you are that you can advance by one step. Is that clear? So that's the principle. So it's considered in mathematics as acceptable way of proving, and we use it very often, and I want to illustrate on a few examples how does it work. Generally, you will see in the structure that this implication is brought, we break this implication in two steps. So instead of telling you the story, I will just illustrate one of the proofs. So, induction. All right. Here is one of the formulas that you had in your Calculus 2, Calculus 1 course. For Riemann sums, you had the following formula. Sum of I squared, where I goes from 1 to n, equals n times n plus 1 times 2n plus 1 over 6. And it says this is true, so we want to prove this statement true for every natural, it's always about natural numbers, for every n greater than or equal 1. So this is the statement, and I'll call it what? Should I call it P of n or P of I? Who's your variable in this statement? N. So this is P of n. So this is statement P of n. So I need to prove 1 and 2. Number 1. I need to check P of 1. So what would that be? Usually I like to write it like this, left side and right side. So how much is left side at 1? It's what? Sum. I goes from 1 all the way to what? How much is your upper limit? But how much is n? So it goes from 1 to what? 1, just one member. I square. And how much is that? Summation of only one member, that's just 1 squared, and it's equal to 1. How much is your right side at 1? 1 times 2 times 3 over 6. What did I get? 1. Are they equal? Yes, so P of 1 proved. Or checked, because there wasn't a proof there. I just calculated both of them, and I got it, that's correct. Basically, if you don't like this summation or all these, this says add first n members. Here I want to add just first one member, so that's just 1. And here comes something that's very important that you remember as a part of the machinery. I need to prove this statement. How do I prove it? Can I pick arbitrary k, or I need do I pick certain k, or I need to prove it for arbitrary k? So let k be arbitrary. And assume P of k. Why? Because I want to prove that this implication is true. What if P of k is false? then implication is true, so I have nothing to worry about. But so whenever you prove implication, you assume that P of k is true, and then you need to prove that what?
P of k
Plus 1 is true. That's why usually I break 2 into 2 steps. I call it 2a. So assume P of k. That's called inductive hypothesis. So what am I assuming? I'm assuming the following, that sum I goes 1 to k I squared equals to k times k plus 1 times 2k plus 1 over 6. I must admit that first time when I saw induction many years ago, I thought that that's pure cheating method. Why? Because look at this. What do I need to prove? I need to prove that this sum equals n times n plus 1 over 2n plus 1 over 6. Do you agree? What am I assuming here? Exactly what I need to prove. So that's the worst thing that you can do about proving. So it looks like it, but it's not. Why isn't it? Because here it is. First, this statement is on this line. Am I proving this line, or I'm now proving this line? So it's completely different line. So now I'm proving these statements. So don't now mix those two lines. What else? I'm not saying that my statement is true for every k. What am I saying? For that I'm at a certain level, k is maybe 17. So I'm saying here, assume that I reached level 17. And I will show you that I can reach which level? 18. Or, would say, but why 17? Is it 27? Yes, if it's 27, so I'm actually proving wherever I am that I can make what? Step up. That's what it is. I'm not assuming the statement is always true. I just say, wherever you get me, I can progress one step. And then that's exactly what we need here. This is called inductive hypothesis. I usually say 2a. So what's important here? Do I need to prove this, or I can use this, that's already established? That's already established. Like on level 17, on level k, I already can use that I reached the level 17. But what do I need to prove then? That I can go where? To level 18. So that's your 2b. And that one you cannot use, you need to prove. I need to prove that left side at the level k plus 1 equals the right side of the 11k plus 1. To make it sure that I will not mix up what I can use and what I need to prove, I like in the beginning to check what I can use and put a question mark. This is not something that's established. That's what I hope to get. And then how do you establish that? That's where the skill comes. And that one, no one can teach you that, because sometimes we do very complicated proofs of induction in some parts of mathematics. If you don't know those parts, we cannot do that proof. So generally, passage from k to k plus 1 is your local knowledge in the discipline. And I will illustrate it in a few mathematical, basic mathematics situations. So here it is. Let me calculate left side at k plus 1. How much is that? So this is what? I might here write things. Shall I write it as sums, or you will prefer me to write dots? Or let me write the sums. On this one and on the next one I'll do dots, since we started the sums. So what's L of k plus 1? Is sum of I squared, where I goes from 1 to where? K plus 1. What did I do? Nothing. In my statement, instead of n, and now I put k plus 1 as upper limit. And basically, I'd like to calculate this. And here is the crucial place, particularly in these problems. How do I calculate now k plus 1? Sum of the first k plus 1 member, hoping maybe to use the information about the sum of first k members. So can I see this somehow within this, yes or no? And that's the main trick. How do you establish connection between k level and k plus 1 level? So is there a connection between this guy and this guy, yes or no?
Yeah, sure.
Oh, I don't want shift because I want them both to start with 1.
Did you say the right side of the first equation plus k plus 1 squared?
Oh, take the last one.
But I'll do that on the next step. First, I want to establish that. So I can say the following. Here I'm running all from the first to k plus first. Do you agree? Can I write that last one separately? So I'll say the following. It's sum I goes 1 to k I squared. And then the last one is what? K plus 1 squared. Do you agree with my interpretation of the sums? So once again, here it says go from 1 to 17. And I said, I'll go from 1 to 16. And I write 17s on its own. Why did I do that? Because do you recognize this guy, yes or no? That's exactly guy from inductive hypothesis. Do I have confirmed how much is that, yes or no? How much is that? And this is where we always put inductive hypothesis as explanation. How do I base my replacement? So that's k times k plus 1, 2k plus 1 over 6 plus k plus 1 squared. So this is the crucial part where you establish connection between two levels. Am I done or not?
No.
Basically, I did the main thing. Now just a little algebra. So I need to do the algebra to show that this will look like this at the level k plus 1. But how do you do that? Usually factoring or something, common denominator. So now it's triviality. Just do a little algebra. And if it helps, I can write what we need to get, or it's fairly simple. What can I factor? First, common denominator. So it's what? And what can I factor out, by the way? K plus 1. So 6 down, k plus 1 ahead. What do I have from the first one? Let's distribute. What do I get? 2k squared plus k. What do I get from the second one? 1k plus 1 is gone. It got 6, so 6k plus 6. This door is still on my way. So here it is, equals. Now I need to factor this out, but you know what I'll do? I'll cheat a little bit. How? I don't like factoring. I can do it, of course. What do I need to get? I write this on the level k plus 1. So what would that be? K plus 2. Do you understand how I got k plus 2? When you put k plus 1 here, and 1 is k plus 2. What should I get here? 2 times k plus 1, and plus 1, it's 2k plus 3. I'll put a question mark because maybe it's not true. I just cheated here. But let me now FOIL backwards. 2k times k is what? 2k squared. 4k and 3k is 7k. 2 times 3 is 6. Is my calculation okay? As I said, since I knew what I need to get, I just wrote it what I expect and then checked it back. It was easier. So what is this? That's my right side at the level k plus 1. So what did I prove here? If they are equal on level k, they are equal on the level k plus 1. And my format I changed, so r of k plus 1. So here it is. And that's how it always goes. So I will do one more with these dots, and it's always how you record, but now I will write it with dots, without sums, and then to practice that, and then we'll see some other situations. Sorry?
How did you get the 2k plus 3 if that's normally plus 1 right there?
Because here it is. I tried to explain it here. First, this is correct. If you FOIL it, you will get, so this is equal to this. Do you agree?
Oh, it's because the n becomes a 2k plus 2.
Exactly.
Okay.
Because when you replace n by k plus 1, 2 times k plus 1 is 2k plus 2, and 1 is 3. So there is a jump by 2 because of doubling. All right, let me write a proof of one of the most famous formulas in mathematics. And I hope you all know it, and probably you know the anecdote connected with it. So here's the formula. Here it is. Prove that for every n, 1 plus 2 plus 3 plus n equals n times n plus 1 over 2. Yeah, so what happened here? Number one, I didn't use sums. What did I use? Dots. Can I write it as a sum, by the way? How would it look? Sum of what? I's, when I starts at 1 and finishes at 10. So if you want to do dots, that's fine with me. We'll come to this formula and discuss it a little more somewhere in chapter 6, I think. 6, yes, when we do recursion. By the way, one of the nice anecdotes in mathematics is that this is the formula invented by, many people say, the greatest mathematician of all time, German mathematician Carl Friedrich Gauss. And people say that he invented it when he was in the first grade of elementary school. So how did he do it? Their teacher was busy, and he asked kids, you ask kids in the first grade to add all the numbers between 1 and 100. And then, so what? So it has nothing to do with induction. So you want 1 plus 2 plus 3 plus 99 plus 100. And he thought they will be busy for like an hour so he can do the paperwork or something like that. But Gauss came in 2 minutes and say, oh, the result is 5,050. And he said, how do you know that? And then he explained what was his reasoning. He didn't do induction. Because induction can never give you the result. Induction can only do the proofs. Is that clear? So what he did, he added these two members and got 101. What about next couple? You go 1 up and 1 down, so sum is the same, so it's also 101. So how many couples of 101s do you get? 50 couples, and that's 5,050. So he just did adding not from left to right, but in a better organized way, and that's basically this. 1 plus n is n plus 1, and you have n half couples, so this is how they came up with this formula. But that's not our goal here. We just want to prove this formula. So how do we prove it? Step 1. Check for n equals 1. How much is left side at 1? How much is this sum when n is 1? And that's why I warned you a minute ago. Because sometimes I saw people saying 1, and this one here, which is 2. No, this sum says stop when you reach n. So when n is 1, as soon as you write 1, you stop. So how much is your left sum at 1? What is it? 1. How much is your right sum side at 1? 1 times 2 over 2, which is what? 1. Is it true? So we checked it at 2. Second A. So now I assume that for certain k, for certain arbitrary k, I already proved what? That's called inductive hypothesis, that the 1 plus 2 plus 3 plus k equals k times k plus 1 over 2. So once again, I'm not assuming the statement I'm proving. I'm just saying that for particular k, I assume that I already established it. And I will show that no matter what that k is, I can go one step more and prove it for which level? K plus 1. So is this inductive hypothesis, yes or no? Can I use it? Yes, so I put check, that's inductive hypothesis. And then on 2b, here's what we do. We usually start with the left side and then try to read the right side. So a left side as k plus 1 equals. What would that be? 1 plus 2 plus 3, da, 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 da. Who's the last one now? K plus 1. And basically, The moment when you solve this problem is when you get rid of the dots. And how do you get rid of the dots? If you connect this and this. But dots are tricky because there are some numbers that are hidden here. Who's hidden here before k plus 1? So it's there. If you want to write it, you can. So what then? Now I recognize all this is already established as being equal to what? Now I use inductive hypothesis. So equals, according to inductive hypothesis, k times k plus 1 over 2. And who else is there? K plus 1. And that's it. You did the main thing. What's left? A little algebra to show what do I need to get, by the way? I need to get k plus 1 times k plus 2 over 2. Is that what I need to get? So let me see if algebra will support that. I'll do common denominator. K times k plus 1 plus 2 times k plus 1. What do I do now? Here it's easy enough. I don't need to cheat like a minute ago. Can I factor out k plus 1? Who's left when I factor it out? Over 2. Which is what? Exactly right side at the level k plus 1. You don't have to use these labels L and R that I do, but it helps to see what is it that you are calculating, what is it that you are assuming, so somehow there is that natural flow from left to right at k plus 1. So once again, what did we prove? That it's true at 1, and then wherever you are, you can get an extra step. That means you will cover them all. All right. Any questions? Is this doable? You are not overreacting for whatever reason. Is it too complicated, or is it too simple, or you don't care? One of those three. Yes.
So is induction specific to like series or sequences like this?
Something that depends on natural numbers, yes. It might be real numbers with the exponent n or something, but things that depend on n. Although people then made some objects in mathematics so that they can do it in some other settings. But generally for us, it's always, if you don't see natural numbers, don't even think about induction. And here I want to prove something. I want to prove that 0 equals 1.
Oh, no.
Why not? All right, here it is. So, I'll say the following. I'll say the following. For every n equals n plus 1, I want to prove this statement. Okay? So here it is. Again, I'll do inductive hypothesis. I'll skip first step. It's trivial. So 2a. So assume that for certain k, I have k equals k plus 1. 2b, I need to prove what? Prove it at n equal at k plus 1. So what is it? Left side at k plus 1 is what? K plus 1. But this k here, by inductive hypothesis, equal k plus 1, and plus, which is equal k plus 2, which is right side at k plus 1. Here it is. What went wrong?
You didn't prove the first.
Exactly. So be careful. It looks like, oh, first one is just plug it in, that's easy. Generally, if you cannot hit the first domino, even if they would fall down, if you didn't hit it, then they will not fall down. So what happened? I didn't check number 1, and if I did at n equals 1, what will I get? 1 equals 2. That's not true. So all this is nonsense. But generally, be careful about it. So it's very important that you check your starting case and then show passes from k to k. If you don't have passing case, then that's not established. Is that clear? So you are basically saying, if I had a healthy start, I would be able to carry it through. But you don't have a healthy start, so that's it. Yes?
So when you ever get a question on a test or quiz saying prove that,
No, this is just a warning. So it's more like, I don't want to spend the whole problem on that. But generally, I want to warn you, because sometimes you are proving something that no one knows if it's true. You're doing some research and you say, oh, let me see. And then you look at the passage and everything and say, oh, look, it's true. But you never test it for some specific numbers. It's not that obvious as here that it's a nonsense. So you are kind of careful. So if you miss your starting case, your induction is not valid. So however easy it looks, it is important to do it. All right. What do we want to do now? So you will see in your homework there will be many problems with these dots, and basically problems with dots, they all look the same. On the next level, you always get the previous sum and the last member, do a little algebra, and be done. I want to show you how all this looks in a little different setting. So here is one of them, similar to what I started there. One in the language of inequalities. A theorem. This is famous Bernoulli's inequality, and he says the following. 1 plus h to the n is greater than 1 plus nh if, let me do greater than or equal, doesn't matter, if h is greater than -1, and n is arbitrary member, and n is an integer, is a natural number. That's famous Bernoulli's inequality. There is some h there. H is any number. H is a real number. But where's your natural number for induction? Who is that? That exponent there. So basically, special case of this one is what? That 1 plus 1 to the n is greater than what? Greater than or equal than what? 1 plus n. And that's what we started. 2 to the n is greater than n. 2 to the n is greater than n. But you can get it for other numbers as well. So how do we prove this? Proof. By induction. So connection between k and k plus first level will be different because this is different part of mathematics. By induction, first, number one, when n equals 1, is it true or not? Left side at 1 is 1 plus h to the 1, which is 1 plus h. How much is right side at 1? 1 plus 1 times h, which is 1 plus h. Did I get the same thing, yes or no? Is it greater than or equal? Yes, they are even equal. So checked. 2a. Assume that for certain k greater than or equal 1, we already established that 1 plus h to the k is greater than or equal 1 plus kh. How do we call this statement? That's what? Inductive hypothesis. Can I use this or not? Yeah, so we assume that that's already established. I'll put a check if you want to make it sure that I can use it. Now I need 2b. That's what I need to prove. So I need to prove. So I avoid to write that k plus first level because students sometimes get tempted to use it. I cannot use that. Is that clear? So if you want to write it, maybe you can write it on the left, outside of your main proof. So it might be a good idea to write it somewhere on the side. You actually want to establish this. 1 plus h to the k plus 1 is greater than or equal 1 plus k plus 1 times h. Is this what I need to establish? So what should I do? I need to prove it for n equals k plus 1. So here it is. Left side at k plus 1 is 1 plus h to the k plus 1. Okay?
Wait,
What?
why again aren't we allowed to write the k plus 1 case?
Because as I said, I want to know what am I expected, where am I supposed to arrive. Someone tells me, I'm here in San Diego driving to Los Angeles, so I'm allowed to have a picture of Los Angeles to recognize it when I get there. So this is just a picture. Don't ever use this. So this is just when we get there, we will know what it is, okay? So here it is. So I have 1 plus h to the k plus 1. So generally what? I want to connect with a guy that I already have under control, 1 plus h to the k. Can you connect this and this somehow using?
1 plus h times it.
Of course. So this is 1 plus h to the k times 1 plus h. This is just pure algebra. Which is greater than or equal than 1 plus kh times 1 plus h. Do you agree with me? Is this correct what I wrote or not? Look at this and at this. Is that correct that 1 plus h to the k is greater than 1 plus kh? Is that true? Here, that's my inductive hypothesis. But then what did I do with it? I multiplied it by 1 plus h. But when you multiply by a negative number, could things flip, yes or no? Yeah, but doesn't matter. Why not?
Restriction.
Exactly. You see a restriction? H is, that's exactly why this is true only for because you can use h to be negative, but not, it has to be above -1, because then 1 plus h is what? Positive number. Positive at least, positive number. So basically what I did, I just took the fact that I already established and multiplied by 1 plus h. Here is where your inductive hypothesis works. And that's it. Now a little polishing. So what do I get here? So now there are no high powers, just maybe I'll distribute. So what do I get? Let me FOIL. 1 plus h plus kh plus kh squared. I like this. Why do I like it? Because I have it on the photo in my car. It's there. That's exactly what I want. 1 plus what? H times what's in the parentheses for those two? When you factor out h, who's left? And that's exactly what I need. But unfortunately, I have a little extra. Is that extra hurting me or not? Is h squared positive or negative? And what about k? Positive. So this is for sure greater than or equal 1 plus h times. So this is extra bonus. I don't need it. So this is the right side. So here it is. We proved if the left side dominates the right side at level k, it will also dominate it on the level k plus 1. And generally, I wasn't sure, I haven't seen it for a long time, should I put greater than or equal or greater? So what? Why is it greater? Because I have kh squared, but it's not greater at which level? The first one. So if you want, we can even say differently, and it would work. I can say greater, but then not start for every n, but for n what? Greater than or equal to what? 2. If n is greater than or equal to 2, you have even strict inequality. So you can adjust. Do you see a different flavor here than with the dots, yes or no? Dots is really cut and paste and do a little algebra. Here what you need is a little skill dealing with inequalities. So you kind of, to multiply by a positive numbers, then if you have an extra, doesn't matter. It still that extra keeps you dominating and something like that. So this is a standard proof in inequalities. So that's one illustration of a proof by induction in a different setting. Let me look at one proof by induction when we have divisibility. So next one will have divisibility. Oh. I forgot to show you this example that's quite important. So I'll come back if I have time, but just it is important that we see one with divisibility. All right, the one in my notes is the same Bernoulli, but in a simpler setting. So this is for h equals 1, and on the board I did a more general one. Here's an interesting statement. Prove that 364 364. Example 4. Prove that for every non-negative integer, for every n greater than or equal 0, sometimes we don't wait to start with 1. Sometimes we start even with 0, or sometimes a little late with 2, 3. So statements are different. Can I have 0 as a starting value, yes or no? Yeah. So label domino with 0, and it works the same way. Can I have starting value -5? Yes, as long as you establish everything above -5. So prove that for every n greater than or equal 0,